Oh boy. Hello, everyone. That lab's being a bit weird, but we don't need it yet. So today, I think will be a little shorter than our last class, because with paired samples t-tests, in a way, I think they're actually simpler or more straightforward than independent samples t-tests. But we'll go through to make sure we understand differences and exactly how they work. And there will be a few unique things. For example, for the effect size with independent samples, it was Cohen's D sub S. Now it's going to be Cohen's D sub Z. But it's not a world of difference. It's still a Cohen D. So we'll go over an example, and what we'll do to hopefully appreciate the difference between independent samples and paired samples is we'll reanalyze the t-test from last week, the Manuscript Harry Potter quote one, but we'll pretend now that it was actually paired samples, and we'll see how that changes things. We'll look at the logic. That's going to be a repeat of last time. We'll delve deeper into the logic of the advanced class. The assumptions, we've actually seen these before, so that will be straightforward. Confidence intervals, there is a bit of a caveat here, but that we'll tackle in the advanced class. There's the new colon B, sub C, and then we'll look at just how we would report this in a manuscript. Before we get going on this, I should mention the assignment. I uploaded the at-home assignment. I uploaded a new version today, with the major addition being section 2 now exists, with questions for paired samples. And I also kind of updated even section 1 to be a little more obvious that for section 1, you're going to use one data file. For section 2, you're going to use another data file. And for section 3, you'll be using both. I'll try to be specific about how you do that for the PhD students. Found a couple of mistakes in section 1. Those have been corrected. So one of them for confidence intervals, I just had a big space, but there should be a confidence interval for choice and one for Stroop, so I made that a little better. And for some reason, in the t-test, in the independent samples, I actually said a paired samples t-test, but you definitely want to use an independent samples t-test on the independent sample section. You might not have even noticed that, but I did fix that. So for master's students, it's just the 2 parts of the assignment, and it's going to be due next Saturday. Well, I guess I should say here, March 12th. For PhD students, there'll be a third advanced section, and that content we'll cover on next month. And then I think after that, it's March break. So, okay. So then we'll be off for a week. Then we'll be back to start our notes. Any questions about our schedule or t-tests from last week? We do have someone missing today. So again, I'm recording the class and I'll upload that to YouTube. You may have noticed there was a link for on Blackboard for last week's class. So if you ever, you're working on this, you want to go back, and that is all archived up on YouTube. So we've seen this before. It's, when to use a t-test. And last week what we saw is, hey, we want to compare 2 different groups. Well, the other way we compare it is if we want to compare the same group in 2 conditions, and that's the topic for this. So this was kind of the example for last week. We didn't look at these data specifically, but if you have one group take a placebo, another group takes L-citrulline, then you want to compare their arterial function. That's an independent samples t-test, 2 different groups. This is a paired samples t-test, or we could also call it a dependent samples. In the ANOVA language, we'll see it called repeated measures, and maybe more broadly, you can call it, within participant, whereas this is between participant. It's somewhat annoying that there's a lot of language that means the same thing. So the strength of women who are postmenopausal is tested. The women then take tocotrienol something, and then their strength is tested again. So it's the same group, so it's dependent or paired samples. And if we did this with independent samples, you can see we're violating the assumption of independence. It's not two different groups, so that's why, well, we violated that assumption, so we're using a different test. So independent samples, just to really force this home, two groups, different people in different conditions. Here, it's the same people who do everything twice, or they go through two conditions. So there are trade-offs to these two techniques, and sometimes you have the luxury of choosing which one to use. Before you run the study, you sit back and think, well, is it better to use independent samples or paired samples? And there's, I think, 4 main points that might lead you to one or the other. And there are times when both are valid, and then you got to figure out what's best in that circumstance. So independent samples, you're going to need twice as many participants. Let's say you need 10 participants. Well, you're going to need 2 groups, so you're going to need 20 total. Independent samples, if you need 10 participants, well, then you only need 10, because people are going to do everything twice. And that leads to the second point, which is a trade-off with the first. So red is bad-ish and green is good-ish. So here, every participant only has to have one measurement. If it's a t-test and over, there might be more, but that's the basic idea. Paired sample, each participant has to be measured twice. So, okay, I only need half as many people, but they have to do twice as much. So, you have to come in twice, once control and once experimental. Here, I'm going to have to find twice as many people, but they only have to come in once each. So that's a pretty good trade-off there. Now, the nice thing, when you test 2 different groups, there's no practice or carryover effects because they're 2 different groups. Whatever you do to this group is completely independent of that group. Over here, there could be carryover effects. And this is probably your largest decision of which type of experiment you want to run. So if I'm doing a learning study, and I bring in a group of participants and they learn a new skill, well, I can't make them unlearn it. So I can't really test them a second time, teaching the same skill in maybe a new way, because they'd be permanently biased by learning that skill. So in that case, I have to do independent samples. But maybe you're giving them, participants, a medication that has a short-lasting effect. Say, let's go with caffeine. We could give you caffeine one day, and maybe that increases your reaction time. That's what we're looking at. We could bring you back a week later, and we don't give you caffeine, and the effect from caffeine a week ago should be gone. So in that case, maybe it is appropriate to use paired samples. Now, one thing we do to help minimize or randomize out the effects of order effects or learning between conditions is, if it is appropriate to do such in a learning study, wouldn't we? But to randomize the order or counterbalance the order. So if you're doing a control, let's say a placebo and a drug, well, half the participants, their first session would be control, second session drug, and then the other half you would do the opposite order. You would start with drug and then go control. And you can even do things like the participant is blind to manipulation, the experimenters are blind to manipulation to help with that. And finally, another key point here is that you have higher statistical power with paired sample t-test and lower statistical power with independent samples. We like higher statistical power, but we need to consider if there's a huge cost for carryover effects that maybe we need to bail out and say, well, we're going to go with lower statistical power because of the middle two dimensions. Any questions on those trade-offs? So you might already be thinking in some of the research that you do, that both might be possible, or if you are, say, testing mice, and at the end of the condition, the mice die, well, you kill them or you sacrifice them. You sacrifice them because you need their tissue. They obviously can't do the other conditions. They don't exist anymore. So we don't always have the luxury of picking between them. but sometimes we do. So why is it more powerful to do a paired samples t-test? Well, here's an example of our independent samples where we've got two groups, different people, and basically we're going to have two types of variance when we compare these two groups. And the more variance we have, the harder it is to see something, to find a significant difference. So when we're comparing two groups, one sort of variance is that, well, this group has no cloaks and this group has cloaks, and that's the essence of the experiment. So we're looking, does it make a difference whether you have a cloak or not? Now, the other variance that we're not really doing on purpose is that these are different participants. So not only is this group different because they're cloaks, these have cloaks, these don't have cloaks, but also this gentleman and this lady, they're also different people. And every person is different, so there's going to be some variability between our participants. So you can think of independent samples as having these two types of variability. The desired variability designed by the experiment by giving one group cloaks, not giving the other groups cloaks. And then also this variability because these are different people in these two groups. So you can probably see where this is going. You know, with paired samples, well, we give this group cloaks, we don't give that group cloaks, that's the desired variability. But now, this gentleman is the same individual in both groups. So he's kind of acting as his own control group, if you will. And that reduces variability, and therefore, whenever we reduce variability, we increase our statistical power. And that's what we'll see today in our example. So when we previously ran the mischief example as independent samples, we saw that the two groups were not significantly different. Today, when we take that same data but pretend it's a paired samples t-test, we'll see that there is a significant difference. It's not always going to be the case, but I think this data was designed, not by me, but by the author, Professor Field, to show that when you switch to paired samples, it's more powerful in general. So we've seen these data before. So now, let's see here. So these aren't different groups. It's the same 12 participants who do this experiment twice. And they probably did it in a randomized or counterbalanced order. So half of them started with the no cloak condition, half of them started with the cloak condition, and then everyone switches. And it's the exact same data. So in no cloak, there's 3.75 mischievous acts. With a cloak, there are more, 5 on average. The question is that significantly different? So in the textbook, you may have seen this language, the long format, short format for data. I always find it a little bit confusing, so we can visualize it here. This is independent samples. And basically, we had 2 columns. The first column says which group is a participant in. 0 was no cloak, 1 was cloak. And then this is the number of mischievous acts by that participant in that condition. And this is the long format because it will go a long way. And when we compare it to how we organize this data for paired samples, well, it's shorter. So we've only gone down to 12, but now it's well, they call it wide format. I guess it's just as wide as the other one. But if we started having more repeated measures, it would get wider and wider. But we'll try to illustrate that again with the ANOVAs. You can see one will be really long and one will be really wide. So now it's 12 participants. They did it twice. So we don't need a coding variable of which group are they in because everyone did this twice. What we don't know here is did they do this one first or that one first? You might want to code for that, but at this level, we're not going to worry about an order effect or learning effect. So now, participant 1, when they did no cloak, maybe that was first, maybe that was second. They did 3 mischievous acts, and then when we gave them cloak, they did 4 mischievous acts. Got that for our 12 participants. So let's run this in SPSS. I'll be curious later to see how it looks in your version of SPSS, and especially what version of Cohen's D that it gives you. So I'm guessing it gives you Cohen's d sub s, and we're actually going to want to use Cohen's d sub z, but I'm curious whether or not that's the case. I do need to contact our IT about why I have 26 and y'all have 28. I mentioned it to Chair Lumpkin, and she was shocked. She didn't know why that would be. Okay, let's see. SPSS. Oh yes. Okay, so here's our data, and I did remember to put these on Blackboard in case y'all want to look at these later. Okay, compare means. So now we want a paired samples t-test. And this is pretty straightforward because we only have two dependent variables here, but we're going to throw them both in. So hey, let's do a t-test where we compare no cloak to cloak. And the options is there's not too much going on yet. Once we get to ANOVAs, there's lots of options we'll wave through. But here we just say okay, and it's going to run it. We just get a couple of boxes, and let's switch to SPSS so we can zoom in on these. Okay, so 3 boxes of results. Let's put this over here. So first we see our means, standard deviation, standard errors. We might want to use those to calculate confidence intervals. It will report some confidence intervals later. We'll get there. The other good thing I always like to check, do we have the number of participants we're expecting? And say yes. We've got 12 participants, 12 in each condition. So just some descriptive statistics there. Here, we see the correlation between, if we imagine our two dependent variables, cloak and no cloak, we have the correlation between them. And it says, yep, we did a correlation based on 12 pairs of data. The correlation, the R value, is 0.806. And is it significantly different? So is it significantly different from no correlation, or 95% of the correlations we expect on random data? Yes, because the p-value is less than or equal to 0.05. And we'll see that this is helpful later when calculating Cohen's d sub z, specifically the R value. So just some descriptions, and then we get to the heart of the test here. So this is the mean difference between the two conditions. It's the same as it was before. This is the standard deviation of the mean difference. This is actually different than we saw last time. So is the standard error of the mean difference. We have a 95% confidence interval of the mean difference. This is helpful. We'll use that in a moment. But the 3 most important things for the statistics of the t-test are the t-value. So it's minus 3.8. The degrees of freedom is 11. The way this is calculated is it's the number of participants minus 1. So we have 12 participants minus 1 is 11. And then, okay, is it significant? This is our p-value, and it's 0.003. That is less than or equal to 0.05. So we are seeing a significant difference between these two conditions. So for reporting that, that's our format for the t-test. Same as the format as last week. Numbers are different. And we are going to learn about Cohen's d sub z because we want to add the effect size onto the end of that. And then here's just our formula for our degrees of freedom, which is quite straightforward. So same data organized differently. Independent sample is not significant because there's more variability. When we reduce the variability by artificially pretending that this is now a paired samples analysis, it is significant because there's less variability and higher power. That will not always be the case, but if you take the same data, you would see a smaller p-value if you reorganize it as paired samples data. Obviously, you can't pretend that your experiment suddenly changed, but if we make this academic theoretical argument, the paired samples t-test is more powerful. Any questions about our example? Yeah.
I had a question. So back when you had the variable view for this, you had it on nominal.
Oh yeah, I may have just had that by mistake. Let's look here. Oh yeah, that's fun.
I mean, it looks like it's okay.
Yes. So SPSS doesn't actually care,
Okay.
which is a little odd. So I really should change this to be scale data, which is its kind of placeholder for either interval or ratio. I mean, it's got nominal, ordinal, and then it just goes scale. which I guess because anything continuous is appropriate for parametric statistics. So that's, yeah, although whatever you set this as, it doesn't like say, hey, you shouldn't be doing that. But yeah, it's probably best to set that. And the other, actually, one thing is with our older data, I realized what's sometimes nice to do is, let's see if I open this up. This one I did. In your assignment data, I forgot to do this, where you can go in and if you have a grouping variable like cloak, and you're like, well, in 5 years, I might need this and forget what 0 and 1 means, you can actually go in and define that. So here I went into, okay, 0 is no cloak, 1 is cloak. And then I think those labels will appear when we run statistics on this, which is easier than just trying to remember what 0 and 1 means. Let's see. It definitely uses them for in ANOVAs. Let's see if it uses them here at all. So we're going to use cloak. Time groups 0 and 1. Let's see if it'll give us some pretty descriptors. No, I don't think it does. Oh, it does. Look at that. So it's instead of just saying 0 and 1, it's used our labels. So that can be a handy way to make your data file easier to interpret. But yeah, if I had changed these to all ordinal, like it would still use them. I don't know if that's good or bad, but that's just how it is. So this is what we found today. So we found it is significantly different. Same data reorganized as independent samples. And what you would always find is it's less powerful. And in this case, we have to be on either sides of that statistically significant threshold to really enforce that paired samples are more powerful. But you didn't have to test every participant twice. So great. I guess more work for the participant. So the logic, we're not going to go too crazy deep on it. It's really the same as what we saw last week and with correlations, that to be significant, we have to draw some sort of line in the sand. Well, what do we mean by significant? And that, what we mean is when the difference between these groups is as large or larger than what we would expect from 95% of the group difference we would find when repeatedly sampling the same population. So we have a population, we take 2 samples, what we would expect is most of the time the difference between those is 0. And I asked MATLAB to do that here with a normally distributed sample that had a mean of 0 and I think a standard deviation of 1. And the most common mean difference between these 2 samples is 0. So it's the same population. But sometimes you get unlucky or lucky, and one sample has a large mean, the other one has a small mean, you subtract them, and there's either a positive or negative mean difference that's out here not 0, but maybe bigger or smaller than 0. And for independent samples, what we do is we can look at the t distribution based on 11 degrees of freedom using this example where there's 12 participants. And that histogram looks exactly like, or has the same shape as our t distribution with 11 degrees of freedom. And then what we can say is, okay, what is the t-value, positive and negative, that will capture 95% of these cases? And the t-value happens to be 2.201, which we can look up from a t-table. So 11 degrees of freedom. We want to capture 95% of the data, or we want 2.5 in each tail. So our critical t-value is 2.201. Now, when we run an experiment, what we basically do for the experiment is say, okay, well, what's the t-value? And if it's within these bounds, say, well, it's not significant because it looks like what we would expect from randomly sampling the same population. But if it ends up further outside of those critical t-values, we'll say, yeah, that's significant. And we might be making a mistake 5% of the time. But we have to draw some sort of line in the sand. And here, with these data, the t-value was 3.8. So that's way out into the left tail. So that's why we conclude that it's significantly different. Any questions about that logic? This might be the last time we see that. I'm trying to remember if we look at, I think we might look at app distribution with the novas. We'll look at the math behind this in the advanced class. So what are the assumptions of paired samples t-tests? Well, the nice thing is they're the same as correlations. The data should be continuous, so either interval or ratio. There should be no outliers, and they should be normally distributed. Last week with independent samples, remember there was 2 extra assumptions, and we don't have to worry about those for independent samples because, well, sorry, with paired samples, they're not independent. And equal variance doesn't apply in this case, in a similar way that it doesn't apply to independent samples when you have equal group sizes. So we don't have to worry about these at all. It's just these 3. We've seen those twice already, so we won't go through those today, but there will be questions on, I guess, at least the latter 2, outliers and normality on the assignment. So pretty much the basic assumptions required of parametric statistics. Confidence intervals. So here's our formula for confidence intervals. And if we go ahead and calculate the confidence intervals for these data, what we're going to see is we're going to get the same confidence intervals we did last week, which is a little weird because remember last week it was not significant, this week it is significant. But the way a confidence interval works is it doesn't involve the differences between independent and paired samples. And to adjust for that takes some effort and some fiddly math, so we'll save that for the advanced class. Just showing the calculation of our confidence intervals, but that's exactly what we got last week. And here, let's just plot it again. So recall for a typical confidence interval, the rule of I is that they will be significant if the confidence intervals overlap by half or less. So here, if we look at this confidence interval, how much does it overlap with this one? Well, it overlaps 80%. So this is like, if it were here to here, that would be 100% overlap. 50% overlap, this one would have to be about here. It's way down here, so that's about 80% overlap. So if we were using the rules of I, we would say that we don't expect these to be significantly different, and yet they are. Why is that? Well, those rules of I for confidence intervals and difference adjusted confidence intervals only work for independent samples t-tests. We can make them work, but we have to use what are called correlation adjusted confidence intervals. The problem is that these confidence intervals that are based on the standard error, or the standard deviation divided by the square root of the number of participants, include the between participant variance, which is excluded in a paired samples t-test. So we can't use the rules of I's with these confidence intervals. So there's 2 solutions. And going back to my last statement there, with paired samples t-tests, remember there's only one type of variance that's important, the actual difference between the 2 conditions. The standard error that we were using to calculate confidence intervals includes this, but it also includes this. And when we look at the math behind the t-test, that variance gets taken out because it doesn't matter for a paired samples t-test, but it's part of the standard error. So that's why we can't use the rules of I for standard confidence intervals. So 2 solutions. One is report the confidence interval of the mean difference. And the nice thing about the mean difference that we saw from last week as well is all you need to see is, does that range include 0? If it does, it's not significantly different. If it includes 0, it is significantly different. And that works out with independent samples and with paired samples. And those values were reported to us by SPSS. So we'll look at that. That's kind of the easiest solution. The other solution is that we have to don't use the standard error, we have to extract from the standard error the between group variance, which doesn't apply to a paired examples t-test, and yet still exists in the standard error. And then once we pull it out, we can use the normal rules of I. And we'll look how to do that in the advanced class. It's not too crazy. I mean, it's not like calculus or anything like that, but there's a bunch of fiddly steps to it. So we'll just look at number 1 today. So here's independent samples t-tests. So this is the one we ran last week. And notice that it gives us a here's the mean difference. Here's our mean difference. So on average, the difference between the group is 1.25 mischievous acts. So there's 1 1/4 more mischievous acts with a cloak, or you could say there's 1 1/4 less or fewer, less without cloaks. And then what's the confidence interval of that mean difference? Well, it ranges from, we'll say, minus 2.76 to 0.26. So for last week, this is our mean difference, and it's 95% confidence interval. Is this a significant difference? Well, we can see from the p-value, no, it is not significant. And we can tell that from this confidence interval because it contains 0. So this goes from -3 to just above 0. 0 is a part of that interval, so it's not significant. If we do the same sort of extraction of confidence intervals, mean difference confidence intervals from this week, we see the mean difference in the mischievous acts, that's actually the same, minus 1.25. But the 95% confidence interval of the difference is has new values because it's excluding, or I maybe say it's only including 1 source of variance and not 2. And now, if we describe that 95% confidence interval of the difference, it goes from -2 to about -0.5. That excludes 0, right? That's the interval, 0 is over here. This one, here's the interval, 0 is right here. It includes 0. This one excludes 0. So just by looking at that, we can use the rule of I that if it excludes 0, it's going to be significant. And we know that's the case because there's our p-value. We already saw it is a significant difference between conditions. So I think for paired samples t-test, that's your easiest bet, is to report the mean difference and its 95% confidence interval. Then you know the rule of I will work regardless of whether it's independent or paired samples, and you don't really have to do any fancy math, as we'll see, well, moderate math, as we'll see with correlation adjusted confidence intervals. The downfall is that you could report a mean for each group, but if you also wanted to throw in the 95% confidence interval, it doesn't really work great here. Works really well for independent samples, especially the difference adjusted one. And we'll look at number 2 in the advanced class. But any questions about relying on the difference, the mean difference confidence interval when doing a paired samples t-test? Again, the nice thing is SPSS. Okay. You can calculate it with the standard formula, but you just need to make sure that you're using, this standard deviation or the standard error of the mean. This is based on the difference, and you can see that it's going to be different for paired samples than independent samples. So let's see, the standard error of the difference here is 0.7, and here it's 0.3. So it is including 1 source of variability. This one is including 2. Okay, effect size. So just like we need to change how the standard error is calculated to only include 1 source of variance and not 2, the same logic applies to the effect size. You will see sometimes in a paired sample, t-test people will report Cohen's d. And if it just says Cohen's d, they probably mean Cohen's d sub s, as calculated last week. But I think it's best, and there's debate over this, to report an effect size that only includes 1 source of variance. And we can do that with Cohen's d sub z. And thankfully, the math is pretty straightforward for it as well. So this is last week, independent samples. We look at the mean difference divided by the pooled standard deviation. That formula is a little messy. If you have unequal group sizes, with equal group sizes, it simplifies, which is nice. Cohen's D sub Z, and a good reference for that is the same Blackwood's article. They go over a few different measures of effect size. I think just for t-tests, I don't think get into ANOVAs. I can't remember off the top of my head. So Cohen's D sub Z, that's what you want to use. At least I would argue you should use for paired samples t-tests. G-Power agrees with me, or at least that's what's in the software. We'll see that in the advanced class. When you do effect size for paired samples t-tests, it will be giving you Cohen's D sub Z, and I think it's labeled exactly as such in the interface. There are 3 ways to calculate Cohen's D sub Z. This is the easiest because it's just the t-value divided by the square root number of participants, so 2 numbers that are in the ANOVA table, in the t-test table. Great. This one is a little longer. These are exactly the same, the values they give you. So faced with the choice, I would go with B0. And then this one is approximately equal to those. And it's a way to estimate the effect size if you don't have all the original data. Why would that be? Maybe you're doing a meta-analysis and all you have is the article where, some articles, they will link to the actual data. Most, I would say, don't. And in that case, you may want to calculate the effect size, maybe the author didn't. But they did report the means, and as long as you have the standard deviations and the correlation between them, you can actually estimate fairly accurately the effect size. The rarest thing I would say is usually that R value is not typically reported. So this isn't always a get out of jail free card, but it's an option. We won't spend too much time on that one because it's a very specific case when you might want to do it. We're typically talking about times when you have your own data or you have the data, so you can use either of these exact formulas, and the easier the better. So here's our first example, calculate Cohen's D sub Z. We need the t-value, so you have to have run the test already. And we're going to divide by the number of participants, which was 12. The only trick here is to remember, when is it 12 and when is it degrees of freedom? Well, here it's n and not the degrees of freedom. There's our t-value, minus 3.804. So we'll throw that in. We'll let PowerPoint do some math for us. Rounded to 2 decimal places. It's minus 1.1. And we can use the same thresholds for effect size as we did last week. I'm trying to remember if that's, let's jump ahead. I don't remember if it's very large. Forget that. Okay, it's between large and very large. I guess I should add D sub Z to that, but you can use these thresholds for Cohen's D sub S or Cohen's D sub Z. So that was nice and straightforward. Let's say you really want to make it hard for yourself. You can use this more complicated formula. So it's still the mean difference on the top, but the bottom, we need to calculate the standard deviation of the difference scores. So it's you can think of this as the standard deviation of the difference. This is the actual formula for it. We won't go through all the steps because instead of calculating this whole formula, SPSS has already given us the standard deviation of the difference. So again, we don't have to go through this challenging calculation with all the individual scores. We can just use the values reported by SPSS. So there's our mean difference. There's the standard deviation of the difference. This is if you want to do it fully, and there's kind of like the long way, and then there's a bit of a shortcut here, but either way, you're going to get the same value. This is the same value reported by SPSS. SPSS just showed 3 decimal places. You can click on it, and it will show you lots of decimal places. but it is 1.138. So regardless of how you calculate this or just look it up, we throw it in there, and we're going to get the exact same value that we saw before. And in the advanced class, I think we'll look at why that's the case. And then our third option, if you do need to approximate this, you don't have the original data, you can use this formula. So you need the mean difference, the standard deviations of each group, each condition. This will be the variance, which is just the standard deviation squared. And then the trickiest thing usually to know is the correlation between them. SPSS gave that to us, but you typically don't report that in the manuscript, unless I guess you have really great foresight that a meta-analysis is coming. But there's our standard deviations, there's our correlation, and the mean difference we've seen a few times is minus 1.25. So we can plug those all in. And if we look at the second last step, this number actually is slightly different. This is exactly the same, that it's still the mean difference, but the part that's approximated is the denominator. And this is a little different than it was before. I'm trying to think, was it 1.1378? Is that a yes? Yes, okay. That is the exact value. This is the approximation. But as it turns out, when we do this and then round to 2 decimal places, we actually get the exact same number. So we got lucky in this case. But if you look at this in more decimal places, it is slightly different. It's an approximation of Cohen's d sub z. So 3 ways, you're probably going to be doing 1 or 2 because you'll have the data, and because number 1 is easier, I would run with that. Questions about Cohen's d sub z? Twice as exciting as Cohen's d sub s. Maybe easier to calculate. Yeah, because you don't need the pooled standard deviation. That was a bit of a hassle. So same thresholds. Put a note to add d sub c to this. Or s. And a comparison to last week. So paired samples t-test more powerful, bigger t-value, smaller p-value, and of course, we should see a larger Cohen's d value. So Cohen's d sub z, 1.1, that's larger than when we reorganize the same data in independent samples, at a smaller effect size of only 0.7. So those things should all be true. Smaller p-value, larger t-value, larger Cohen's d value. I guess it's not completely fair because these are actually, the math isn't exactly the same to them. So our last section is just, how would you report this in a manuscript? And this is pretty similar to last week. So the key change is we're not talking about 2 groups anymore. So I highlighted that. And we're talking about the same group in 2 conditions. So you might not even talk about the group when you talk about, well, there's a cloak condition and no cloak condition. So the number of mischievous acts in the condition without cloaks were compared to the condition with cloaks with a paired samples t-test. So we were talking about conditions, and now it's a paired samples t-test, not an independent samples t-test. And to be clear about what we're reporting, I say the effect size was reported using Cohen's d sub z. There's my reference in case the reviewer is unaware of that notation. And there are different ways that this is reported. D sub z and d sub s, I think, are the most common. The mean difference and its 95% confidence interval was reported. And we're using this because, remember, the rule of I that we saw still applies here. Does it contain 0 or does it not? If it does, not significant. If it doesn't, significant. You could report the standard 95% confidence intervals. You just need to make sure when you're reading it, or I guess you also hope when someone else reads it, they don't apply the independent samples or rules of I because they don't work for paired samples. Here, we're not going to have that problem because the rules of I do work for the mean difference. two different options here, and this is really based on what do you want to emphasize? Do you want to emphasize that there's more mischievous acts with the cloak? Is that kind of the most important thing in your experiment? Or do you want to emphasize that there are less mischievous acts without a cloak? And sometimes it might not matter. Other times, you might want to be emphasizing one more than the other. So there are 1.25. Here's that's the mean difference. This is it's 95% confidence interval. More mischievous acts in a condition with cloaks than a condition without cloaks. And then, comma, and then our statistical support. We have our t value with the degrees of freedom, our p value, everything rounded to 2 decimal places, and then our effect size, Cohen's d sub c. Or if we really want to emphasize that there are less mischievous acts without a cloak, we could write the sentence in the opposite order. And that if this is the most important finding in your results or in your manuscript, so we have the text, but you might want to include a table or a figure. This might become more relevant as our analyses get more complex. Because if we did have a table, there's maybe not too much more to add. But you could do a figure, well, I guess we don't want to do the 2 bars, we want to use the difference. But if this is, the major result of the experiment, then often a table or figure is good to highlight those. I'm sure we've all read a paper where, we read the intro and the method, we get to the results and we just look at the figures because we're kind of taught to put the most important results there. Any questions about manuscript or section? It's not too complicated, right? It's very, very similar to last week, and maybe fewer things to worry about, especially with the assumptions. And yeah, Cohen's d sub z is actually probably easier than Cohen's d sub s. So the in-class assignment is online. It's a different file, data file from last week. Those are up on Blackboard. So the file you want to use is one that's paired t-test with your name on it. And let's just see here. Let's look at it quickly together. It's not as long either. So I'm asking for the confidence interval of the difference, rules of I. Calculate Cohen's d sub z. And when anyone runs their data, if they want me to take a peek at their, I know the new version actually gives you Cohen's d, but I think it's maybe d sub s. I'd like to know. And then to report the statistical results of your t-test.